The moon. It hangs in our night sky, a familiar, silent companion. For centuries, we've gazed at it, dreamed of it, even walked upon its dusty surface. We've written poems about its ethereal glow and told stories of its mysteries. But the moon is no longer just a poet's muse or a distant landmark for fleeting visits. It's on the verge of becoming something more, something dynamic and profoundly different. Nations are now looking up with new eyes, their gaze sharpened by ambition. They see not just ancient rock and lifeless regolith, but a frontier brimming with untapped opportunity. China and Russia, two significant global players, have joined hands. They are planning something truly audacious for our lunar neighbor. What is this grand vision, you ask? Imagine a permanent human presence on the moon, not just a brief sortie for planting flags and collecting samples, but a lasting settlement, a true outpost. How would such a lunar colony survive? More importantly, how would it thrive in such an alien environment? The answer, according to this ambitious Russo-Chinese blueprint, lies in the boundless power of the atom. We're not talking about modest solar panels struggling against the long, cold lunar night. We are talking about nuclear energy, a consistent, reliable, and incredibly potent source of power, enough to keep the lights on, life support systems humming, and crucial scientific experiments running, day and long dark night. This plan is undeniably bold. It represents a significant leap, a quantum jump, from previous lunar missions that have captured our collective imagination. We all remember the grainy images of the Apollo landings, a monumental triumph of human ingenuity for their time. We see the steady stream of data from ongoing robotic missions, diligently mapping terrain and analyzing samples. But installing a nuclear reactor on the moon? That elevates the game to an entirely different level of ambition. It signals a profound shift in thinking, from pure exploration to potential long-term habitation, and even industrialization. It speaks volumes about long-term strategic goals being set for decades to come. This is a clear statement of intent. This extraordinary plan, to deploy nuclear power on the moon, isn't just another routine rocket launch. It isn't merely another sophisticated satellite being placed into orbit around some distant celestial body. The very idea of harnessing nuclear energy on the lunar surface, a project spearheaded by two major global powers like China and Russia, resonates deeply. It captures our collective imagination unlike many other scientific endeavors. Simultaneously, it raises immediate, profound questions that echo around the globe. It sparks intense debate among scientists, policymakers, and the public alike. It compels us all to pause and think critically about the future unfolding before our eyes. What does it truly mean to bring such potent, transformative technology to a pristine, untouched world like our moon? The intense global fascination also stems from the undeniable geopolitical undercurrents. When nations like China and Russia, with their complex histories and shared strategic interests, decide to collaborate on such a grand, technologically advanced scale, the world instinctively pays close attention. This is a partnership with deep roots and potentially far-reaching implications that extend well beyond the realm of space exploration. This ambitious lunar venture is not taking place in some isolated political vacuum, far removed from terrestrial concerns. Instead, it clearly reflects the shifting alliances, the burgeoning ambitions, and the evolving power dynamics that characterize our world today. The profound silence of space might soon be punctuated by the echoes of earthly strategic maneuvers playing out on a new, grand, and very visible celestial stage. There's an undeniable sense of wonder here, of course. It's the kind of awe that science fiction has fueled for generations. But this wonder is tinged with a palpable apprehension. Nuclear power, as we all know, carries a dual legacy here on Earth. It offers the promise of immense, almost limitless energy, a key to unlocking new frontiers. Yet it also presents profound risks and complex challenges that demand careful management. Transplanting this powerful technology to the unique environment of the moon opens up a veritable Pandora's box of possibilities, both incredibly wondrous and deeply worrying. For decades, we've consumed stories of sprawling lunar colonies and advanced technological marvels in space. Now, elements of those imaginative fictions are inching ever closer to becoming science fact. Ultimately, this is why the world watches with such rapt attention, with a mixture of excitement and concern. The moon, our constant celestial companion, has silently witnessed the entirety of human history. For millennia, it has been a source of wonder, a subject of myth, and a beacon in the velvet darkness of night. Its silvery glow has inspired poets, guided travelers, and fueled an insatiable curiosity within the human spirit. Its proximity, a mere 384,000 kilometers away, makes it an almost irresistible target, a cosmic neighbor tantalizingly within reach. This closeness doesn't diminish its alien nature, rather it amplifies the challenge and the allure. The dreams of touching its surface, once confined to folklore and fiction, became a reality decades ago. Now those dreams are evolving, transforming into aspirations for something far more enduring, far more ambitious. The era of fleeting lunar visits, of planting flags and quickly gathering samples is yielding to a new paradigm. The Apollo missions were a monumental achievement, a testament to human ingenuity and courage. But today's lunar ambitions stretch far beyond those initial sorties. The current focus is shifting towards establishing a sustained presence, learning to live and work in that alien environment for extended periods. This renewed interest is not merely a nostalgic echo of past glories. It represents a calculated strategic pivot towards a future where the moon is envisioned as an integral part of humanity's expanding sphere. Nations, including the potent partnership of China and Russia, no longer see the moon as just a historical landmark, but as a vital asset, a platform for future endeavors. One of the primary drivers for this renewed lunar focus is its undeniable scientific value. The moon is a remarkably preserved archive of the early solar system, its ancient surface holding secrets to planetary formation and cosmic evolution. Within its craters, particularly those near the poles that lie in perpetual shadow, scientists anticipate finding vast quantities of water ice. This frozen water is not just a scientific curiosity, it represents a critical resource for future missions, potentially providing drinking water, breathable air, and even rocket propellant. Furthermore, the moon offers an unparalleled platform for astronomical observation. Its far side, permanently shielded from the cacophony of Earth's radio emissions, is an ideal location for telescopes to peer into the deepest recesses of the universe, promising new discoveries about its origins and fate. Beyond the scientific quest, the moon serves as a formidable catalyst for technological advancement. The extreme challenges inherent in operating on the lunar surface, the vacuum, the abrasive dust, the wild temperature swings, and the radiation demand innovation. Engineers and scientists are pushed to develop new breakthroughs in robotics, advanced materials, closed-loop life support systems, and crucially, resilient energy solutions. The solutions engineered to overcome these lunar hurdles often find valuable applications back on Earth, benefiting various industries and improving our quality of life. It is this potent combination of profound scientific inquiry, strategic foresight, and the relentless human drive to innovate that firmly places the moon at the center of our current spacefaring ambitions, a challenge that leading space powers are now embracing with renewed vigor and determination. The moon's significance extends far beyond its own rocky sphere. It is increasingly recognized as a crucial gateway, an essential stepping stone for humanity's grander voyages into the cosmos. Consider the monumental challenge of sending crewed missions to Mars, our rusty red planetary neighbor. Such an endeavor requires immense resources, complex logistics, and technologies pushed to their absolute limits. Utilizing the moon as an intermediate base, a sort of forward operating post in space, could significantly enhance the feasibility and sustainability of these ambitious interplanetary journeys. It offers a relatively nearby location to assemble and launch spacecraft, to test vital systems, and to acclimate crews before they commit to the long, arduous transit to more distant worlds like Mars. The practical advantages of using the moon as a launch pad are compelling. Its gravitational pull is merely 1/6 that of Earth, meaning significantly less energy, and therefore less propellant, is required for a spacecraft to escape its grasp and venture into deep space. This lower gravity could allow for the launch of much heavier payloads, or reduce the overall mass of missions departing for Mars or the asteroid belt. Furthermore, the moon lacks any significant atmosphere, eliminating the aerodynamic stresses and atmospheric drag that spacecraft experience when launching from Earth. Imagine constructing and fueling a Mars-bound vessel in lunar orbit, or even on the surface, perhaps utilizing resources extracted directly from the moon itself. This vision begins to reshape the entire economic and logistical framework of deep space exploration. Moreover, the moon presents an unparalleled training ground for astronauts destined for long-duration missions. Living and working on the lunar surface for extended periods would provide invaluable real-world experience in coping with conditions beyond Earth. Astronauts could master techniques for operating in partial gravity, learn to mitigate the risks of radiation exposure, and develop strategies for dealing with the psychological strains of isolation, all within a communications latency of mere seconds from Earth. Any mistakes made, any lessons learned on the moon, are far easier to manage and rectify than they would be millions of kilometers away, en route to, or on the surface of, Mars. The moon, in this sense, serves as a demanding but essential teacher, preparing us for the greater trials that lie ahead in our cosmic journey. This fundamental role as a proving ground is a core reason why nations are channeling significant investment and intellectual capital towards lunar endeavors. It's a strategic investment in building future capacity, in accumulating critical operational know-how, and in systematically reducing the inherent risks associated with venturing further into the solar system. Every piece of equipment tested, every habitat module deployed, every operational challenge successfully overcome on the lunar surface contributes directly to the broader human aspiration of becoming a truly multi-planetary species. The moon offers a unique, almost perfect blend of relative accessibility and formidable adversity, making it the ideal laboratory for refining the tools and techniques necessary for our interplanetary future. It is where humanity will learn to take its first confident steps before attempting to stride across the vast expanse of the solar system. Section 3. Strategic High Ground Resources, Research and Geopolitics. As humanity extends its reach beyond Earth, the moon is inevitably becoming an arena where pragmatic and at times contentious considerations of strategy and resources come into sharp focus. The allure of the moon is no longer solely about the romance of exploration or the pursuit of pure scientific knowledge. It is increasingly viewed through the lens of strategic advantage, a celestial high ground that offers tangible benefits to those who can establish a meaningful presence there. In an era marked by renewed great power competition on Earth, the ability to operate effectively on the moon, to utilize its resources, and to project influence from its surface is rapidly emerging as a new significant metric of global standing and technological prowess. What unfolds on the lunar landscape will undoubtedly resonate with and potentially reshape terrestrial power dynamics. The potential for lunar resources is a powerful magnet drawing nations and private enterprises alike. Foremost among these is water ice, now confirmed to exist in permanently shadowed craters near the lunar poles. This ice is more than just frozen water, it is a critical enabler for future space activities. It can be harvested and processed to provide drinking water for astronauts, oxygen for life support systems, and, crucially, hydrogen and oxygen for manufacturing rocket propellant. The advent of in-situ resource utilization, or ISRU, promises to revolutionize the economics of space exploration, potentially making missions far more sustainable and less reliant on expensive Earth-launched supplies. Beyond water there is talk of helium-3, an isotope rare on Earth but believed to be abundant in lunar soils, which proponents suggest could fuel future clean fusion reactors, though its practical extraction and use remain subjects of ongoing research and debate. The moon also presents unique strategic advantages for Earth observation, deep space monitoring, and communications. A lunar-based observatory, for instance, could offer unparalleled, continuous views of our home planet, unimpeded by atmospheric interference or cloud cover, providing valuable data for climate studies and disaster monitoring. Similarly, radio telescopes on the moon's far side would be shielded from Earth's radio noise, enabling unprecedented sensitivity and listening for faint cosmic signals. While international space treaties like the Outer Space Treaty of 1967 prohibit the placement of nuclear weapons or military bases on celestial bodies, the distinction between scientific, commercial, and dual-use strategic infrastructure can often be nuanced. Establishing a significant, technologically advanced presence naturally provides a commanding vantage point in every conceivable sense. Ultimately, the race to establish a foothold on the moon is also about shaping the future. The nations or international consortia that succeed in building the first permanent, self-sustaining lunar bases will inevitably play a leading role in defining the norms, regulations, and unwritten rules for all subsequent lunar activities. Being physically present, demonstrating advanced technological capabilities, such as deploying a nuclear power source, sends an unmistakable message of capacity, long-term commitment, and serious intent. This emerging dynamic is not simply about another round of exploration, it's about laying claim to a stake in the future development and governance of an entire celestial body. The grand chessboard of global geopolitics is undeniably expanding its dimensions, and the moon is rapidly becoming one of its most crucial and contested squares. Section 4. A new era of lunar permanence laying the foundation. The Sino-Russian plan for a nuclear-powered international lunar research station aims for permanence. Previous moon missions were transient, astronauts arrived, researched, and returned. The new vision involves a continuous human and robotic presence. This shift demands long-term sustainability, self-sufficiency, and off-world habitation. Transforming the moon into a growing home requires mastering its harsh environment. The lunar night, lasting 14 Earth days, challenges solar power systems. Lunar dust infiltrates mechanisms and poses health risks. The moon's surface is exposed to high levels of cosmic and solar radiation. Robust habitats and reliable energy sources are essential for survival and productivity. This pursuit of lunar permanence drives innovation and technological breakthroughs. Scientists are developing closed-loop life support systems and using lunar regolith for construction. A robust energy infrastructure is crucial for powering habitats and research. The moon serves as a testing ground for technologies needed for Mars and beyond. Establishing a permanent presence on the moon lays the foundation for humanity's future in space. It signifies a transition from exploratory visits to becoming true denizens of the cosmos. The moon is the first critical outpost on this extraordinary journey. Section 1. Forging a New Lunar Destiny, the ILRS Vision. At the heart of China and Russia's lunar strategy is the International Lunar Research Station, ILRS. The ILRS represents a vision for a permanent scientific outpost on the moon. It signals a serious commitment to a long-term presence beyond Earth. The ILRS is designed to operate autonomously and support human crews eventually. This grand project began in March 2021 with a Memorandum of Understanding between CNSA and Roscosmos. This collaboration aligns resources, expertise, and geopolitical aspirations. The ILRS aims to rival or surpass other international lunar efforts. The project is a multi-decade endeavor with carefully planned stages. It includes scientific research, resource extraction, and human habitation. The ILRS will evolve from a robotic outpost to a hub of human activity. China and Russia invite international partners to join the initiative. This collaboration suggests an alternative model for international cooperation in space. The ILRS is not just a scientific project but also a geopolitical one. It signals multiple paths and competing visions for humanity's future on the moon. The ILRS is a bold step towards a permanent lunar presence. Section 2. A phased approach. Building the lunar outpost step by step. The ILRS requires meticulous planning and step-by-step execution. The timeline extends over a decade, with milestones in the mid-2030s and beyond. The phased approach starts with robotic reconnaissance and ends with a crewed research facility. Each phase builds on the last, ensuring challenges are addressed and technologies proven. The initial phase focuses on reconnaissance and site selection. Robotic missions like China's Chang'e and Russia's Luna missions map the lunar surface. The lunar South Pole, with potential water ice deposits, is a key focus. The construction phase begins in the late 2020s, assembling core infrastructure. Key systems for energy, communication, and scientific investigation will be established. The final phase, starting around 2030, involves utilization and expansion. The ILRS will conduct scientific research and prepare for crewed missions. The station will eventually host astronauts for long-duration stays. The ILRS will evolve into a fully functional research hub. This phased approach ensures a sustainable and permanent lunar presence. Section 3. Mission Objectives. Unlocking lunar secrets and sustaining life. The ILRS aims to conduct profound scientific research across multiple disciplines. It will study lunar geology, internal structure, and volcanic history. Analyzing lunar samples and seismic data will unlock secrets about the moon and the solar system. The ILRS will also serve as an astronomical observatory. A core objective is the exploration and utilization of lunar resources, ISRU. Prospecting and extracting water ice is a priority for long-term sustainability. Water can be broken down into hydrogen and oxygen for air, water, and rocket propellant. Producing propellant on the moon could revolutionize space exploration. The ILRS will test ISRU technologies. The ILRS aims to pave the way for a sustained human presence on the moon. It will develop life support systems, radiation shielding, and robust habitats. The ILRS is a stepping stone for learning how humans can live off Earth. It will verify technologies essential for future deep space exploration. Section 4. The Nuclear Heartbeat Energizing a Permanent Lunar Future. The ILRS's feasibility relies on a dedicated nuclear power source. The nuclear reactor is the primary energy backbone for the station. Without reliable power, a permanent lunar outpost remains science fiction. The nuclear solution underscores a commitment to long-term lunar presence. The reactor must be compact, robust, and largely autonomous. It must operate reliably in the extreme lunar environment. Safety is paramount, with comprehensive shielding and fail-safes. The moon's long nights make solar power impractical. Nuclear fission offers continuous reliable energy. This power is essential for life support, heating, and scientific instruments. The nuclear power system is a critical milestone for the ILRS. Its successful deployment will transform the ILRS into a dynamic research outpost. The reactor is the heart of the station, enabling continuous research and resource utilization. It powers the dream of a permanent future on the moon. So, we've explored the grand vision of China and Russia, their ambitious international lunar research station. We've touched upon the strategic allure of the moon itself. But a critical question hangs in the vacuum. Why the focus on nuclear power? Why choose this complex, often controversial technology for a lunar outpost? The answer begins not with human ambition, but with the fundamental, unyielding nature of the moon itself. Imagine our familiar earthly cycle day gives way to night, usually for a manageable stretch of hours. Now, picture the moon. Its day is long, about 14 Earth days of continuous harsh sunlight, but then follows its night, an equally long expanse of 14 Earth days plunged into profound unbroken darkness and unimaginable cold. This isn't just a brief interlude, it's a fortnight of absolute black. This extreme lunar day-night cycle presents an immediate, formidable challenge for any sustained presence. For decades, solar power has been the go-to energy source for satellites and robotic explorers venturing through our solar system. And why not? The sun bathes our planetary neighborhood in abundant energy. On the moon's sunlit side, solar panels can indeed soak up this energy, converting photons into precious electricity. We've seen it work for smaller rovers and landers, but when that 2-week night descends, those same solar panels become dormant, silent observers in the frigid dark. The flow of energy simply stops. This isn't just a matter of inconvenient darkness. Temperatures plummet dramatically, potentially reaching below -170 degrees Celsius, posing a severe threat to any unheated equipment or habitat. But wait, you might ask, what about batteries? Can't we just store enough solar energy during the long lunar day to last through the equally long night? That's a perfectly logical question. We use batteries with solar power all the time here on Earth. However, the scale of the challenge on the moon is vastly different. To power a substantial lunar base with life support for astronauts, heating systems to combat the cryogenic cold, scientific instruments running complex experiments, and potentially energy-intensive mining operations for a continuous 14-day period would require an absolutely colossal battery farm. The sheer mass and volume of such batteries would be astronomically prohibitive, making them incredibly expensive and difficult to launch from Earth and land safely on the moon. Therefore, for any civilization aspiring to establish more than just a temporary campsite, for any plan that involves a continuous year-round operational presence with significant energy needs, the solar plus battery model begins to buckle under the immense strain of the lunar night. The moon's environment itself dictates a need for something more robust, something that doesn't flinch when the sun dips below the horizon for 2 long weeks. This unforgiving cycle forces us to look beyond conventional solutions, to seek an energy source that can provide a constant, unwavering stream of power, irrespective of the sun's position in the lunar sky. The quest for true lunar permanence demands an energy heartbeat that never falters in the face of that deep, enduring darkness. The decision to embrace nuclear power for the International Lunar Research Station isn't just about overcoming the lunar night, It's also intrinsically linked to the sheer scale and ambition of what China and Russia envision. This isn't a plan for a modest, automated weather station or a small passive observatory. The ILRS is conceived as a comprehensive scientific research facility, designed for complex experiments and, crucially, with the long-term goal of supporting human crews. Such an endeavor inherently comes with a voracious appetite for energy. Think about the basic needs for human survival in such an alien environment. Continuous life support systems are paramount, providing breathable air, managing carbon dioxide levels, recycling water, and maintaining a stable internal atmospheric pressure. Then there's the critical need for heating, to keep habitats and equipment within operational temperatures against the backdrop of the moon's extreme cold. Beyond these fundamental survival requirements, the scientific and operational goals of the ILRS multiply the energy demands considerably. Sophisticated scientific instruments, from spectrometers and drills to astronomical telescopes and geological analysis tools, often require significant and stable power to function optimally and gather meaningful data. Robust communication systems, linking the lunar base with Earth and coordinating activities across the lunar surface, also draw a steady current. Then consider the planned robotic operations rovers traversing the landscape, robotic arms for construction and maintenance, and potentially the heavy machinery required for in-situ resource utilization, ISRU. If the base is to, for example, mine water ice from shadowed craters and process it into rocket fuel, that alone represents a massive energy expenditure far beyond what simple solar arrays could sustain through the night. The aspiration for permanence is a keyword here, and it fundamentally reshapes the energy calculus. Unlike the Apollo missions, which were short, targeted sorties with limited power needs, the ILRS is designed for continuous, long-duration operation, evolving over years, even decades. This means the lights can't just go out for 2 weeks every month. Scientific experiments might need to run uninterrupted for extended periods. Life support for a potential crew must be unfailingly reliable, 24/7, 365 days a year. The energy infrastructure must not only meet current demands but also possess the capacity to support future expansion and increasingly complex activities. The power system is not just an auxiliary component, it is the lifeblood of the entire station, determining its ultimate capability and longevity. So, when we consider the ambitious blueprint for the ILRS, a bustling hub of scientific research, a test bed for resource extraction, and a future home for astronauts, it becomes abundantly clear that a mere trickle of power simply won't suffice. The energy requirements are substantial, continuous, and likely to grow as the station matures. The dream of establishing a truly functional long-term lunar foothold, a place where humans can live and work productively for extended periods, hinges critically on securing a power source that is not only reliable through the long lunar night, but also potent enough to fuel these grand ambitions. This profound need for a robust and unwavering energy heart is what steers the conversation decisively towards more powerful and persistent solutions. Faced with the twin challenges of the relentless lunar night and the substantial energy demands of a permanent base, nuclear fission emerges as a compelling, perhaps even indispensable solution. The most fundamental advantage of a nuclear reactor is its ability to generate a continuous, unwavering stream of power, completely independent of sunlight. Whether the sunlit plains are bathed in harsh radiation, or the landscape is plunged into cryogenic darkness for weeks on end, a fission reactor steadily produces electricity. This constant output is precisely what a lunar outpost like the ILRS needs, a reliable energy source that ensures life support systems keep humming, scientific instruments keep collecting data, and essential heating protects against the brutal cold, day in, and desolate night out. This around-the-clock reliability is the cornerstone of nuclear's appeal for lunar colonization. Another critical factor that makes nuclear power exceptionally well-suited for space applications, especially on the moon, is its incredible power density. Nuclear fuel, such as uranium, packs an immense amount of energy into a very small amount of mass and volume. To put this into perspective, a compact nuclear reactor, perhaps the size of a small car or even smaller, could generate megawatts of power. Achieving the same continuous power output with solar panels and the requisite battery storage for the 14-day lunar night would require covering vast areas with solar arrays and deploying an enormous, heavy battery farm. The sheer mass difference is staggering. This high power density translates directly into significant savings in launch costs, as every kilogram launched into space is incredibly expensive, and simplifies the logistics of transporting and deploying the power system on the lunar surface. Furthermore, modern designs for space-rated nuclear reactors, often referred to as small modular reactors, SMRs, are engineered for long operational lifespans. These systems can be designed to operate continuously for many years, potentially a decade or even 15 years, without needing refueling or extensive maintenance. This longevity is a perfect match for the goal of establishing a permanent, long-duration lunar presence. It minimizes the reliance on frequent and complex resupply missions from Earth solely for power system components, allowing resources to be focused on other critical aspects of base development and scientific research. A power source that can be deployed and then trusted to operate reliably for a significant portion of the base's projected lifetime is an invaluable asset in the harsh lunar environment. Finally, there's the crucial aspect of autonomy and resilience. Nuclear reactors designed for remote applications on the Moon or Mars can be engineered to be highly autonomous, capable of operating with minimal human intervention or even telerobotic oversight from Earth. This is particularly important for the initial phases of the ILRS, which will likely be predominantly robotic. These reactors are being designed to be robust, capable of withstanding the extreme temperature swings, the vacuum of space, and the pervasive lunar dust. Their inherent design features, coupled with advanced control systems, aim to ensure safe and reliable operation, providing that unwavering heartbeat of energy that a pioneering lunar outpost will so desperately need to survive and ultimately to thrive in an otherwise inhospitable world. When we weigh the options, considering the grand scale of ambition that China and Russia have laid out for their International Lunar Research Station, the choice of nuclear power begins to look less like a mere preference and more like a fundamental necessity. For a project that aims for long-term, continuous operations, for a base intended to support complex scientific research, resource utilization, and eventually human crews, the limitations of other power sources become starkly apparent. The 14-day lunar night is an unforgiving adversary for solar power, and the sheer energy density required to sustain a thriving outpost through that darkness makes reliance on batteries an impractical dream due to their immense mass and volume. Nuclear fission, in contrast, offers a solution that directly addresses these core challenges head-on. It's important to acknowledge that solar power certainly has its place in space exploration, and it will undoubtedly continue to power many lunar endeavors. Smaller landers, short-duration robotic rovers, or even supplementary power systems for specific sun-dependent tasks can effectively utilize solar energy. However, when the mission objectives escalate to establishing a foundational, baseload power supply for a continuously operating multi-module research station with plans for future expansion and human habitation, solar power, even augmented by batteries, simply struggles to meet the persistent high-level demand. The ILRS is not envisioned as a temporary campsite. It's the cornerstone of a permanent lunar presence, and such permanence requires an equally permanent and powerful energy source. The adoption of nuclear power for a lunar base represents a significant technological step, a leap that genuinely unlocks a new echelon of capability for humanity in space. It signals a move beyond the constraints that have historically limited the scope and duration of off-world missions. By providing a reliable, long-lasting, and powerful energy source, nuclear reactors can transform the Moon from a place of fleeting visits into a realm of sustained human and robotic activity. This is about enabling a new era, one where we can conduct more complex science, seriously explore the utilization of lunar resources like water ice, and realistically plan for the day when astronauts can live and work on the Moon for extended periods, laying the groundwork for an eventual self-sustaining presence. Ultimately, the answer to why nuclear? For the Moon, particularly in the context of ambitious long-term projects like the Sino-Russian ILRS, is etched in the unyielding physics of the lunar environment and the unwavering energy demands of establishing a truly permanent foothold. It's a choice driven not by whim, but by a pragmatic assessment of the challenges and a bold vision for what humanity can achieve on its celestial neighbor. Nuclear power offers the promise of a constant, reliable dawn for lunar exploration and settlement, an energy heartbeat strong enough to sustain our most audacious dreams for a future beyond Earth. For China and Russia, it appears to be the key to unlocking that future. Building a nuclear reactor here on Earth? That's already a monumental undertaking. It involves years, often decades of meticulous planning, thousands of brilliant minds. Precision engineering pushed to its absolute limits. Now pause for a moment. Imagine transplanting that entire colossal challenge to the desolate alien surface of the moon, 250,000 miles away. The difficulty doesn't just double, it skyrockets. It becomes an Engineering Everest. First, consider the reactor itself. It can't be the sprawling giant we know on Earth. Lunar reactors must be marvels of miniaturization, incredibly compact yet astonishingly powerful. Why this obsession with size? Because every single kilogram launched into space costs a fortune, an astronomical sum quite literally. So engineers face an immense, intricate puzzle. How do you shrink complex reactor cores, cooling systems, and shielding, all without sacrificing critical safety margins, or the vital power output needed for a lunar base? This isn't just improvement, it demands true, groundbreaking innovation. Then comes the terrifying prospect of launch. Getting this concentrated nuclear heart off Earth, safely, securely, that's the very first and perhaps most nail-biting hurdle. What if something goes catastrophically wrong during ascent? The reactor, even before it's ever switched on, must remain intact. It must be designed to withstand incredible forces, to ensure absolute containment of its nuclear materials. There is zero room for error when radioactive elements are involved. Public trust and planetary safety are paramount. Engineers design for multiple interlocking safety layers, preparing for scenarios they hope will remain unthinkable. And if the launch succeeds, the perilous journey has only just begun. The reactor must then endure the harsh transit, a silent voyage through the cold, unforgiving vacuum of space. It will be bombarded by cosmic radiation. It will experience wild, disorienting temperature swings, from the sun's unfiltered glare to the deep chill of shadow. The delicate machinery, the precisely engineered components, all must survive this gauntlet, arriving on the moon not just in one piece but fully functional, ready to be carefully awakened, ready for its critical, life-sustaining mission in a new world. Once safely delivered, the reactor faces the moon itself. And the moon, our silent sentinel, offers no gentle welcome. It's a world of brutal, stark extremes. Imagine the lunar day searing unfiltered sunlight, heating surfaces up to a blistering 120 degrees Celsius, or 250 Fahrenheit. Then, as the long night descends, unimaginable cold. Temperatures plummeting to a cryogenic minus 180 Celsius, or nearly minus 300 Fahrenheit. Materials expand, contract, strain, and potentially crack. Cooling systems designed for Earth's relatively mild variations will be pushed to their absolute operational limits. Survival in this thermal battlefield is a constant, relentless engineering war. Then there's the invisible threat, radiation. Earth, thankfully, cocoons us. Our atmosphere and a powerful magnetic field act as vital shields, protecting us from the worst of space radiation. The moon has no such planetary defenses. It lies exposed, naked to the cosmos. Cosmic rays, energetic particles from distant supernovae, bombard it relentlessly. Solar flares, sudden violent eruptions from our sun can unleash intense bursts. The reactor itself, a source of radiation, needs its own robust armor. Heavy, dense shielding is absolutely essential, not just to protect its own delicate electronics, but to safeguard the wider lunar base and any future human inhabitants. And we cannot forget the dust. Oh, the lunar dust. It's not like any dust on Earth, it's a superfine talcum-like powder called regolith, but its particles are incredibly sharp, like microscopic shards of glass, forged by eons of meteorite impacts. Worse still, it's electrostatically charged by solar radiation, so it clings. It sticks to everything. Everything. It will try to infiltrate every seal, every joint, every moving part. Clogging mechanisms, abrading sensitive optical surfaces, degrading thermal controls. This pervasive, insidious menace is a persistent technological headache. A silent saboteur working against every piece of hardware. Finally, consider the profound isolation. If a critical component falters, if an unexpected problem arises, there's no quick response engineering crew just down the road, no overnight delivery of spare parts. The Earth, our familiar blue marble, is a distant beacon. Help, in the form of a new mission or direct human intervention, takes days, possibly weeks. Therefore, the lunar reactor must be exceptionally self-reliant. Highly autonomous diagnostic systems will be crucial. It needs the intelligence to monitor its own health, to identify faults, perhaps even to attempt rudimentary self-repair. The reliance on robotic upkeep and remote commands is immense. Section 3. Operational hurdles, distance, deployment, and the unknown. Managing a complex nuclear system from afar, that introduces another layer of daunting complexity. Communication, even at the speed of light, isn't instantaneous. Signals take precious seconds to travel, from the moon back to Earth, and then for commands to return. For routine system checks or planned adjustments, this delay is manageable. Engineers can factor it into their procedures. But what about in an emergency, a sudden critical malfunction? Those few seconds can stretch into an eternity, when swift, decisive action is paramount. Control systems must be incredibly sophisticated with onboard intelligence, capable of autonomous responses to protect the reactor and the base. And how can we be truly unequivocally sure it will all work? Before this multi-billion-dollar nuclear heart ever leaves Earth, it must undergo the most rigorous, exhaustive testing imaginable. Engineers will strive to simulate every conceivable lunar condition: the vacuum, the temperature swings, the radiation, the dust. But can we ever perfectly replicate the moon's unique environment here? Can we foresee every subtle interaction, every potential failure point? Creating a perfect Earthbound imitation of another world is almost impossible. There will always be lurking uncertainties. Some operational gremlins might only reveal themselves once the reactor is truly there, on that distant, dusty plain, under alien skies. Landing the reactor safely is a monumental achievement in itself, but it's just the prelude to the next intricate act deployment. Imagine the delicate robotic ballet required to carefully unpack the reactor from its landing vehicle, to transport it, position it with pinpoint accuracy, perhaps to partially bury it for shielding or connect it to pre-laid cables, to link it seamlessly with the base's power distribution grid. All of this likely performed by advanced, semi-autonomous robots. Each maneuver, each connection, is a high-stakes operation, in an environment where a dropped tool or a misaligned component could have cascading, mission-threatening consequences. There is very little room for error, and woven through all these known challenges is the ever-present whisper of the great unknowns. The history of space exploration is a testament to this. It's filled with unexpected phenomena, with surprising discoveries, with challenges that no one could have fully anticipated. We meticulously plan for all the risks we can identify. But what about those unknown unknowns? The unique ways nuclear technology might interact with the pristine lunar environment over decades, the unforeseen geological quirk or the subtle effect of lunar gravity. The moon still guards many of its ancient secrets. This Sino-Russian venture, for all its planning, is truly pioneering, a bold, audacious leap into profound technological uncertainty. Section 1. The geopolitical chessboard extends to the stars. The moon, once a symbol of universal wonder, a shared heritage for all humankind, is rapidly transforming before our very eyes. This Sino-Russian nuclear initiative is a bold stroke, a powerful move on a newly expanding global stage. It signals more than just scientific curiosity. It's a clear, undeniable statement of geopolitical ambition. The silent, cratered plains are becoming an arena, a new frontier for earthly rivalries and power plays, where influence is projected not in miles but in future possibilities. We see the battle lines subtly being drawn, not with soldiers, not yet with overt weapons, but with treaties, alliances, and grand technological declarations. The US-led Artemis Accords chart one path for lunar conduct, inviting nations to join a framework for peaceful exploration and utilization. Now, China and Russia, with their International Lunar Research Station, offer another, a parallel vision backed by formidable state power and distinct partnerships. These are not just competing scientific roadmaps, far from it. They represent potentially divergent sets of rules, of norms, of influence, for who gets to do what and how on this new celestial frontier. Success in this high-stakes lunar game is potent currency. It can reshape perceptions of global leadership for decades to come. Demonstrating mastery over nuclear power on the moon, for instance? That's a technological triumph with profound symbolic weight. It projects an image of dynamism, of advanced capability, of far-reaching vision. Beyond mere prestige, there's the undeniable lure of future lunar resources. Water ice for rocket fuel, perhaps helium-3 for future fusion energy. Securing access, establishing a significant presence, is seen as key by leading nations. a strategic imperative in a resource-conscious and increasingly competitive world. This is about far more than just pure science. It's about future terrestrial and celestial dominance. And so, inevitable questions arise, pressing and uncomfortable ones. Does this bold lunar plan, this nuclear gambit, edge us closer to conflict, towards the potential militarization of a domain once envisioned as peaceful? The Outer Space Treaty of 1967 explicitly forbids military bases and weapons of mass destruction. But what about dual-use technologies, enhanced surveillance capabilities, strategic positioning? The lines between civilian and military applications can blur easily, almost imperceptibly. A nuclear reactor is primarily for power, for sustaining life and science, yes. But the infrastructure, the advanced know-how, the very presence itself, all contribute to a significant strategic advantage. A watchful eye from above. The quiet, simmering tensions on Earth could find a new, unsettling echo in the silent heavens. Section 2. Redefining rules and responsibilities in the cosmos. This grand lunar ambition, this audacious nuclear power play. It doesn't just challenge the known limits of engineering, it fundamentally tests our existing frameworks for space governance. The Outer Space Treaty of 1967, a cornerstone document of the space age, was born from a different era, a Cold War détente, a nascent understanding of space. It wisely declared space the province of all mankind, free for peaceful exploration and use. But does its vintage wisdom, its broad principles, fully cover this new, unfolding reality? Nuclear reactors operating on the moon, plans for large-scale resource extraction? These activities push the boundaries and probe the ambiguities of established international space law. New interpretations, detailed elaborations, or perhaps entirely new treaties seem urgently needed. The moon, with its finite, incredibly precious, and strategically located resources, especially that vital water ice, believed to be concentrated in permanently shadowed polar craters. Could it, if we are not careful, become the stage for a new tragedy of the commons? A celestial gold rush with nations and private entities scrambling for their share? Who truly owns these lunar resources? Who possesses the right to extract them? And under what specific conditions? For whose ultimate benefit should they be used? The Sino-Russian ILRS, by its very nature and its pioneering ambition, will set precedents. Its actions, its operational claims, its physical and technological footprint on the lunar surface will inevitably shape the de facto answers to these profound and pressing questions. Establishing norms through practice, perhaps even before clear de jure rules are universally agreed. And what of our solemn responsibilities as stewards of the cosmos, even of a seemingly lifeless, barren world like our moon? Deploying nuclear technology, however advanced and carefully engineered, carries inherent risks. The possibility of accidents, of unintended radioactive contamination, however statistically remote, must be soberly, transparently, and internationally considered and mitigated. The pristine lunar environment, a unique scientific archive of solar system history, undisturbed for eons, deserves our most careful protection from irreversible harm or widespread disturbance. Pioneering nations, those pushing the boundaries of the possible, bear a heavy burden of responsibility. To operate with utmost caution, with full transparency, and with deep, intergenerational foresight, ensuring that short-term national gains do not inadvertently lead to long-term celestial degradation for all. Ultimately, this ambitious lunar venture, powered by the atom, forces us to look inward, to reflect deeply on the kind of future we are actively choosing to build beyond Earth. Are we destined to merely export our terrestrial rivalries, our age-old conflicts over territory and resources, our unfortunate historical tendency to exploit new frontiers without full consideration of long-term consequences? Or can this new chapter in space exploration, this bold reach for another world, inspire something better within us? A model where even competing powers can find common ground, establish shared principles of conduct, perhaps in shared safety standards, in collaborative scientific endeavors, in robust emergency assistance protocols. The legacy of this nuclear-powered lunar base will be written not in months, but over decades and generations. Will it be a beacon of isolated national achievement, a symbol of a new space race, or a difficult yet crucial step towards a truly spacefaring and hopefully wiser global civilization? Section 1. The lunar atom, dawn of a new era or a precipice of peril. And so, we stand at a fascinating juncture, don't we? Our moon, that familiar celestial orb, is being reimagined. It's transforming from a silent, distant witness in our night sky into a dynamic stage for human ambition. The audacious plan by China and Russia to power a lunar outpost with the very heart of the atom is a profound testament to this shift. It's a concept that, just a few short decades ago, might have seemed confined to the vibrant pages of science fiction novels. Yet, here we are. The blueprints are coalescing. The engineering challenges are being confronted. This is no longer mere speculation. It is rapidly becoming a tangible, unfolding chapter in humanity's ongoing cosmic narrative, a bold leap into a future we are only just beginning to define. This Russo-Chinese vision for a nuclear-powered international lunar research station is undeniably bold. It's incredibly ambitious. It speaks volumes about a future where humanity's reach extends far beyond the cradle of Earth, aiming for a sustained, perhaps even permanent, off-world presence. Such an undertaking pushes the very limits of our current technological capabilities, demanding innovation at every turn. It signals a strategic commitment to long-term space exploration and utilization that is truly monumental in its scope. But this grand ambition, this powerful reach for the lunar surface, also carries with it an immense weight. It carries the weight of responsibility, the weight of unforeseen consequences, and the heavy scrutiny of a world watching with a mixture of awe and apprehension. The implications of this lunar power ripple outwards, far beyond the realms of pure science and engineering. They touch upon the complex tapestry of global geopolitics, potentially redrawing alliances and igniting new forms of competition, this time played out on a celestial stage. As new capabilities are demonstrated 384,000 kilometers away, new questions inevitably arise back here on Earth. How will the existing international frameworks, like the Outer Space Treaty, adapt to these novel activities? Will nations find pathways towards genuine cooperation in this new lunar era, sharing knowledge and resources for the common good? Or are we destined to see terrestrial rivalries simply mirrored or even amplified in the vacuum of space, turning the moon into yet another contested frontier? Ultimately, the path ahead remains shrouded in a cosmic mist of uncertainty. This nuclear-powered lunar base, this bold statement of intent from China and Russia, could indeed become a shining beacon. A beacon of human ingenuity, of peaceful international collaboration, and of unprecedented scientific discovery. It might truly unlock the secrets of the moon and serve as a vital stepping stone for our journeys deeper into the solar system. Or could it represent a perilous step into uncharted territory, a realm where the rules are still unwritten and the potential for miscalculation or conflict looms large? The answer, as always, will depend on the choices we make, the wisdom we collectively summon, and how the nations of Earth decide to navigate this extraordinary and challenging new dawn in space. The universe waits,